is in contrast to basic methods of econometrics, because you have many kind of things which you input. It doesn't learn automatically from the data. If it learns automatically from the data, then well, econometrics is as good as the same as machine learning. So machine learning tries to learn automatically. That's once again. So there are three kinds of learning in machine learning. One is broadly three kinds of learning. One is supervised learning. This you already know because you do regression, you do classification. So the broad difference in regression and classification is, in classification you have categories like dogs and cats, dog versus cats, rich versus poor, or something like that. And you classify them into some categories. That is classification. So these are called supervised because they have labels. You know what are rich, what is poor, what is dog, what is cat. Now regression, on the other hand, looks at a continuous variable on the dependent side. That means income in rupees or dollars. So for example, you have somebody having 100,000 income. That income 100,000 is in dollars. So that amount, and it could be 100,000, 2, or 52,000 or 96,000. So these are in the interval scale because there can be values. So there could be values in between two values. Unlike a dog and a cat, there are only two categories. Or dog, cat and horse, there are three categories. So in contrast, in regression, you can have several values between any value. So between 1001 and 1002, there is 1001.5. So you can have some values. So they are in the interval scale. So you are trying to predict a number, a value. So that's regression that you already know. So I'm just trying to mention here that you have basically two kinds of supervised learning, regression and classification. And why we call it supervised? Because they have labels, they are numbers. We know the correct value, true value. And classification, we have labels like categories. And regression, we have values. So in a sense, you look at it that if you have the income of a person, an income can be a regression. But if you classify them into rich and the poor, high income or low income, then it becomes a classification because there are categories instead of a value. So that's the difference between regression and classification, because and these comprise supervised learning because there are ground truths, there are values or categories to predict. We know what are the real ground truths are. Ground truths versus predicted, truth versus predicted. Because you have truth values and you're predicting something, so you can tell the error, the difference in error in prediction. So long as you have the ground truths, they are supervised. But unsupervised is a different game. If you do not know the ground truth, if you do not know the real values, and you are trying to see how, then you don't know what errors you made, right? Because so long as the data tells you that this is a cat and you have learned the image of a cat, that's good. But so long as nobody tells you whether or not it's a cat, then how will you know you predicted correctly? If you have such a niche situation where you do not know the ground truth of the data, so if there is no ground truth, it becomes difficult to learn. For example, if the baby is never told what is a cat, then understanding what is a cat really is so difficult because the baby has no clue that this is called a cat. Now, if you have such a situation where there is no ground truth, that is unsupervised learning, where there is no ground truth. So what are the basic tasks that can be done for unsupervised learning? One example could be clustering. For example, if you have 100 students in a class and you want to group the students in some way, so you neither know how many groups they are, nor you know what types of groups they are. So suppose nobody tells you that you have to group them into boys and girls, and nobody tells you that you can group them into high scoring or low scoring or medium scoring or nobody tells you have to group them based on grades, you don't know the groups. So, and you don't know how many groups. And that is clustering. And that is unsupervised because there are no labels. There is no ground truth. You just have to figure out your own without labels. That's clustering. And there's another example of, there are many examples. Another example is dimensionality reduction. So you have a lot of data, you just want to reduce the dimension. Suppose you have, so in machine learning we typically deal with say thousands of dimensions. Now in econometrics traditionally we would deal with maybe 7, 8 variables, 9, 10 variables and try to select some variables to reduce the dimension, maybe 10, 15 variables too. But in machine learning it's okay to have thousands of variables. So you can do it with, you can use the same method in econometrics too, but in machine learning we can deal with a large number of dimensions. Now humans really can't deal with too many dimensions. We can only see 3 dimensions, and nature has limited dimensions too. It is said that you can have 7 dimensions or so, or around. So humans can only see 3. But data can be in thousands of dimensions. If you look at a gene, human genome, then it has probably 5,000 or more dimensions. Now the point is, and there can be many more. When you look, so it depends on what level of work you do, how many dimensions you're working on. So the dimension, so you may like to reduce the dimensionality. And in the traditional econometrics, what you have is, if your number of rows cannot exceed the number of columns, you know that. So therefore, for example, otherwise it will be, if there's a problem of identification. So if the number of rows is less than the number of columns, you cannot run a regression. Suppose you have 20 variables and you have 15 rows, you can't run a regression on it. It has to be greater than or equal to the number of columns. And that's what, usually you have 3, 4 variables or 5, 6 variables and maybe lots of data. Generally it's not the issue, but sometimes you have this issue. For example, I mentioned about the genome, and if there are something like 5,000 variables, and but you need to have 5,000 gene data to run on it, right? 5,000 gene data is a lot of amount of data. It's difficult to have that much of data. If you're working on 15,000 variables, you need 15,000 data points, which is really challenging. So that's why you have bioinformatics in these cases. You really can't use things like these, basic regression. Those things won't work because there are too many variables and too few data points. Now in this case, what do? There are many approaches. One of them is dimensional reduction. There is feature selection, some more. And in machine learning, we have something known as the SVD, singular value decomposition. I'll mention it later. But the point I'm trying to drive home is, dimensional reduction is a kind of unsupervised learning because you don't have labels. There is no truth, count truth, because you don't know the intrinsic dimension. The intrinsic dimension could be 4, but you don't know. You don't know how many dimensions and what the dimensions are. So therefore it is unsupervised because you don't know the ground truth. And the third is reinforcement learning. In reinforcement learning, what you try to do is think about it as a robot trying to figure out through a maze. So there will be walls and it's trying to figure out. Or think about it that you have a vacuum cleaner which is automatic. The vacuum cleaner figures out where to go. You don't have to drive it. So if the vacuum cleaner is figuring out through a maze of walls, so when it's about to come very near a wall, then its sensors tell it, hey, you're about to hit. And so it gets a feedback when it is closer to a wall or an obstacle. So when it comes closer to a wall and an obstacle, it gets a feedback. So there is a sense of rewards where you know it has progressed around a direction, so it is rewarded. So reward is like built into the algorithm. So basically what it tries to do is it gets reinforced when it takes a correct decision. So it keeps learning automatically as it progresses through a system of rewards and penalties. The point here is there's a learning here, because at every step he takes, the robot takes, he gets new information and he tries to learn, okay, this is the correct direction. And then he hits something or comes close to something, then he changes his direction, okay, he learns, okay. So he learns how to drive. So self-driving cars, vacuum cleaner robots are examples of reinforcement learning, because it tries to learn automatically. Now that's the point, automatically learn. You just give it data and it will learn automatically. There's no human intervention there. Give it a program, it will learn automatically how to drive or automatically how to clean which direction to take in for the automatically cleaning robot. What I'm trying to mention here is this kind of learning is known as reinforcement learning. Does it apply to finance? Of course. For example, you have algorithmic trading. In algorithmic trading, you buy and sell or hold. Suppose you're buying a share stock and you want to know whether you want to sell or hold or buy. So it learns, because when it makes a small mistake, it learns, well, this is something I learned, I have to be careful next time. I mean to say, I'm verbalizing it like a human, but it learns in terms of the loss or a profit it gained. From the loss, it tries to see, oh, I made a lot of profit there. So it tries to say, this is a good direction. So it will pick up features automatically. Now what features? That's different. It will learn on its own some features which humans cannot easily decipher. So you cannot easily find out what the features are really, because it learns a system of a large number of weights, and those weights determine the system. So basically when you look at it, when we say learning, if you try to think, what are those features that it learned? It's difficult to verbalize, because sometimes we can, for example, if you have a principal component analysis, PCA, which you know. So this is not a machine learning method, it's a closed form method. Now in PCA, you know, what we do is we reduce the dimension, but we resolve it into components. But those components are not in the same space as the original data, right? So because they are not in the same space as the original data, so you have already resolved it into components, right? So you may want to verbalize, like say, well, this component probably means this. Component 1 can be said as having a majority of components for this, majority of factor loadings for this. So you can say component A means this, component B means this, component C means this. But it's not in the same as the original space, data space. So what I'm trying to say is, what are those features? Now coming back to machine learning, what are those features is difficult to verbalize. So it's like a black box. So I'll discuss this more again as I discuss on the limitations, but I just want to mention here is there are a system of weights that it learns, and those weights determine how it's going to determine how well it does. So it learns a lot of weights, a lot of biases, a lot of weights, and then it tries to do a good job in regression, classification, clustering, dimension reduction, or reinforcement learning. So it tries to do a good job in its types of tasks. But the point I'm trying to drive home is, it automatically learns, does an extremely good job in its prediction. The prediction is generally really very high, most cases. So we talk about something like above 95-99% most of the cases. So you can say that generally traditional methods can't do so well, That's because there isn't any learning that's happening. So here you are learning from it and improving through experience. Okay, so I move on. Deep learning. Now, deep learning is probably the sexiest part of machine learning, because these days, there's a lot of, I would say hype, but I would say also there's a lot of demand for jobs, for research positions in deep learning, because deep learning has really transformed machine learning and a lot, or made a huge. Machine learning has made great strides with deep learning. Some examples are like multi-layer perceptrons, convolutional neural networks, recurrent neural networks, long short-term memory, autoencoders, deep leaf networks. I'm just mentioning them so that if ever you ever hear them, you would know these are deep learning, deep reinforcement learning, generative adversarial networks, and so on. So I'm mentioning them because whenever you see a word deep inside it or networks inside it, newer ones, you would find them most likely they are deep neural networks. This is what is a lot of work is happening, and these deep learning methods have really proliferated in all domains. You even think about you. So it's not just econometric, economics and finance, but all domains, and a lot of it in medicine and business, and so you can think like electricity load prediction or something like that, or environmental systems and many things. So everywhere they have really proliferated. The reason is the extremely high level of accuracy and the level of detail they go into by capturing the system. So that's that's the reason why deep learning has really shot off so well, and lots of jobs and research opportunities here. So understanding deep learning requires generally some skills. Using the tools is easy, but generally you need to know a little bit of statistics, little bit of mathematics, little bit of computer science, of course. So it is, you could say, an interdisciplinary area. There's more of computer science there, but in the sense that the code is mostly these days the language of choice is Python in deep learning, because it's probably the easiest programming language, because most of the practitioners are non-computer science background of non-computer science. Therefore, it seems like Python has emerged as a language of choice, and it's very, very easy to learn. But then, so which means that, and most of the econometrics experts in econometrics are gradually moving to deep learning these days in research. So you may also want to consider it to see, hey, what's it? Let me find out. So I would invite you to explore deep learning. So what are the challenges of econometric methods? Again, as I mentioned, number of variables, but more importantly, non-linearity. Now, econometric methods do take on non-linearity. There are many methods in econometrics which handle non-linearity. For example, you have piecewise regression. So those kind of, there are many methods which do challenge it, but that's limited. But machine learning methods by design are non-linear, and it can take on, you can give more non-linearity to it. You can add non-linearity to it by your choice. For example, you have piecewise regression, but you cannot add your linearity of your choice. But in machine learning methods, you can add non-linearity of your choice as much as you want. You can make it more and more detailed. You can choose the depth and the width of your models. So, in contrast with limited non-linearity, there machine learning is all non-linear and very, very extensively, and you can customize it how long, how deep you want, and how more non-linear you want. Again, as I mentioned, the
Excuse me?
untied. I'm sorry.
Yeah,
Yeah.
so are you changing the slides? Or you are on the
Yes,
first
I
slide
changed the
itself?
slide just now. Are
But
you
it
able
is
to
not
see?
showing.
Oh, wait
No,
a second. Let me see here. Are you seeing challenges of econometric methods here?
no, it's on the
No,
first
sir.
slide itself.
Oh gosh, just a second. Let me go back. Okay, let me try this. Okay, let me go back and go on. Is this visible now?
Yes, sir.
Was this visible earlier?
Thing, it was just the first slide.
Oh gosh, so this was not visible, right? I'm so sorry. I
No.
apologize. No, sir. Okay, so okay, so you have any questions on this? I discussed it, of course. So you are listening, but do you have any questions on this slide? All
So
quiet means I understand no questions, or
the
okay,
questions can be taken later
later on.
in
That's
the
right.
Q&A.
Okay, fine. So just in case I mention about this part about machine learning, what it is, it's a proper subset of AI. More importantly, it automatically learns and improves from experience. These are the types I mentioned: supervised, regression versus classification. They are called supervised because they have labels. I mentioned of unsupervised because there are no labels, no ground truth. Examples I gave: clustering, and I mentioned about dimensional reduction, and then I discussed about reinforcement, the robot thing, and whether it works through a maze. And I mentioned about algorithmic trading and as example of reinforcement learning. And I mentioned about deep learning in general being the driver for recent advances. And I mentioned about deeper layers and I mentioned about limit number of variables being greater than number of observations, then you're in trouble. In that case, you might like to do a dimension reduction, of course. I mentioned about limited non-linearity because you do have nonlinear approaches to regression in econometrics, such as piecewise regression and so on. But I mentioned they're limited. But I mean, and there are other methods too, of course, in nonlinearity. But they're limited. In the case of neural networks, they are or deep neural networks. You can it is inherently non-linear, and you can add more non-linearity, you can add more layers, you can add more depth of breadth and depth of non-linearity. Okay, so this was what I was discussing so far. I guess I was sharing the slide, but I I was not sharing my whole screen. I probably shared only one tab, and that is why the issue. I apologize for missing out. Is this clear? Just a second, let me just check. Am I sharing? Is this visible?
Yes, sir, it's visible.
Okay. So I move on. Let me put it on the full screen mode here. Okay. Once again, did the slide change?
Yes, sir.
Okay. Thank you. So the third thing is that um, geometric objects, such as, okay, when you have in basic methods like if you wanted to do multiple regression or many more other kind of basic econometric tools, what you would do is in those kinds you mostly use things like geometric objects such as covariance matrices and all. Now when you have rows and columns and you are working on covariance matrices, because you're working on rows and columns only, you cannot recognize topological relations in networks easily. It becomes difficult. What I mean to say, you can have graphs. Suppose you have graphs. Your data is inherently graphical. Think about your social media networks. If you look at the social media network, the graphs of the social media networks, you will see that they are not really like tables. So you have, it's because you will have different persons linked to different other persons. Somewhere you have dense linkages, somewhere you have in social media of your Facebook or LinkedIn. In Facebook, you may have a strong relationship with another person. You chat a lot with them, and then you have a kind of weak relationship with another person via somebody else. So those network structures have a lot of information too. So look at it in this case, for example, even if the international trade data. So the international trade data, even though you can plot it in terms of tables, you can show international trade in terms of tables. You have which country exported to what country, how much volume, that's fine. But we are missing on the graphical relationships. You may miss on that. So because it doesn't show or describe or work on the topology. So what I mean to say is, actually the relationship is better done in a graphical form, because you have each of these nodes and these edges. The thicker the edges, more the relationship. So if there is a huge amount of trade between India and US in textiles, for example, suppose you have something like that. Suppose 6200, and you have in chapter 262 woven garments, and you are for 6200 you have a huge amount of trade, volume of trade. Now, if you want to show it in a graph form, then you will have a thicker graph edge on that, and then you can, and then it will capture much more relationships than you would otherwise think in terms of rows and columns. The point is this, in terms these, we may think that it is easier to work on tables because of covariance matrices, but when there is a topology, there are limitations. So again, in case of, whereas in machine learning, there are methods to handle graphs in different way. Now, those methods could be used in econometrics as well, but you can learn on those networks well too. So the learning is something which the machine learning provides very well. Now, the other thing is that interaction effects. So if you think about it, if you do, for example, multiple regression, and you have 4 independent variables and 1 dependent variable, again trade, if you have volume of trade determined by income, in exchange rate, and something else, 3, 4. So suppose you have these things, real exchange rate, and then the GDP of countries determining, and 2 more variables determining the volume of trade. Now there could be a multiplicative interaction effect too, because you have x1, x2, x3, x4 determining y. Now there could be a multiplicative thing like x1 into x2 determining y. Now, so typically your regression model is additive. Now when you have multiplicative interaction effects and all those things, so basically those are not really modeled well because we miss them out. We can have models which can build on, which can have multiplicative interaction effects, but that will be, the number of such effects is very large. So for P features, the number of multiplicative interaction effects are 2 to the power P, or nearly 2 to the power P. So if you have 10, it will be 2 to the power 10. It will be nearly 2 to the power P. So therefore, that's a large number of multiplicative interaction effects. So your model doesn't become scalable. You cannot really work on the scales when you have a large number of variables on a narrative model. So the point I'm trying to drive home is, by design, neural networks, deep learning takes on these, because you can have a dense layer where each node interacts with each other node in a dense layer. So which means there's a large number of parameters, and generally any deep learning models have thousands and millions of parameters, and quite unlike our regression models where you have limited number of parameters, maybe 6-8 parameters if there are 6-8 variables. So you have them, but they have thousands and millions of parameters which are used in machine learning models, particularly deep learning models. So therefore, the multiplicative interaction effects are not really an issue, because it sees the relationship between all these various kinds of nodes. And besides, the big issue is it picks up unobserved variables. In the case of most econometric methods, though there are some which do take unobserved variables, latent variables, there are latent class models too, but mostly they look at work on observed models. So, but in the case of machine learning and deep learning models, they are inherently designed to capture unobserved models. They are inherently designed like that. So you don't look at the observed variables only, you look at latent or hidden variables too. What I mean to say is, if you want to know what determines volume of trade, for example, you could say from theory we know GDP determines it, because you have and then you have the gravity model, which says the distance determines trade. Then you have exchange rate determines trade. These things you already know from theory. And now, but you see, well, there could be hidden unobserved variables which we don't know. That's where machine learning does very well, because it tries to figure out what are the features. Features are different from observed. Features can be unobserved. So it tries to find out what are the features from the data. So there's something known as feature selection, feature extraction. So so the models try to understand the features, underlying hidden features in the model. So that is where it comes in. And that's make it very different from traditional econometric methods, because you try to find out hidden features and you don't need to worry about interaction effects. Now, the next thing is stationarity is something, when you are doing a time series and you're working on, you have unit roots tests, ADF tests, and you have non-stationarity issues, and you know that if there is a unit root, then it's not stationary, it's non-stationary, you rule that out. But you can also have non-stationarity without having a unit root, and so on. So there are many issues. And even with the ADF test, augmented Dickey-Fuller test and others, that has limitations too. It doesn't really work well necessarily in all kind of data. There are limitations. And stationarity may be failing in many kinds of data. So when you have non-stationarity data, though there are methods in geometric methods to do it, but there are limitations a lot. However, machine learning methods and deep learning methods are inherently designed to take on any kind of non-stationarity. It can take on these. Now, even those things like trend data and other things, it still works. So nothing is perfect, but still it does better when there is non-stationarity. And then finally, basically overall, if you want to have a look, basic econometric methods do not learn the structure of the data. You give it a model and it tries to predict, tries to tell you what is the model, how well the model behaves. So you have to give it a model, and then it tries to understand how it behaves. Whereas in the case of machine learning models, It tries to learn the structure of the data. Give it some. So given that you give it another data, it will still try to learn. So basically, you can do a good job in generalizing the model, and so that makes it so different. Okay. Challenges of ML methods. Is the slide visible? Just a double check.
Yes, it's visible.
Great, thank you. So having said that, all the brouhaha about, well, machine learning is great, machine learning has limitations too. It's not perfect. And the biggest challenge is data requirements. It is data hungry. It needs a lot of data. So if you give it a little data, so why does it need a lot of data? Because it has to learn. If you don't give it data, how will it learn? Suppose you give it just 10 points of data and you expect it to learn. Well, how can it learn from 10? It needs more. Maybe give it 100 or 1,000. So more and more data give it, better it does. I think that's a fair assumption too, because unless you give it data, how will it learn? So that's probably a fair requirement. However, sometimes humans do better. For example, if I saw a pretty actress in the movie, and I see her once, it's possible just looking at her once I can recognize her again, because she was pretty, I know her face, I pictured it, and the next time I saw it, I recognized her. I didn't need a lot of data. Humans can do a great job in identifying by looking at once. It can do very well, because humans have developed a kind of, already it has a developed model of recognizing people. Now machine learning won't be able to recognize that pretty face by just looking at once. You need to give it a lot of data to recognize a particular person. So therefore, humans can sometimes do very well in this. Now, but the human has also learned over years of recognizing people. So that way you can say that human has already taken a lot of data. Now, what I'm trying to drive home is that one of the challenges of machine learning methods is data requirement. Though there are some methods such as one-shot techniques, and there are techniques which can take on few-shot learning too. So give it a few shots of data, it can still recognize. There are some models, machine learning models, which can work on less data too, and those are called one-shot learning and few-shot learning. That's also there. However, broadly, they need a lot of data. The second thing is that reinforced bias. If your data has a bias, then your machine learning method can't do any better because it has a bias. And that's a big issue. Why? Because think about hiring people. So suppose you are hiring people based on a machine learning method, an AI method. They call it an AI method to hire people. So what do they do? Well, given a lot of millions of people applying, it can figure out who is the best fit. Now, how did it figure out? Basically, they figure out because you gave it some label that these people were great. This is this kind of profile we want. And now in that profile, suppose the person who has told the ground truth and the preferences, he gave 10 examples of what is a good candidate to hire. Now of those 10, there are 8 males and 2 females only. Now that means there is a bias already, because they showed that these 8 men were good and were preferable, and 2 females only out of 8. So there is a gender bias. Now if there is a gender bias in it, then your machine learning model won't do any better because there is a gender bias already in the data. Similarly, for example, if you have typical example of race. Now if a particular race, so you have in US white, black and brown and all kinds of races here, for example. So if you have, just for example, a particular race, say XYZ, say Y, has been found to have committed more crimes. So 80% of the crimes are done by people of Y race, for example. So if you see a person who is of a Y race, then the model will typically highly likely pick him up for being arrested. So there's a bias inherently in the model because it has a gender bias, it has a race bias. I mean, that's where it reinforces bias if there's an existing bias. Now, that's also, I would say, unfair to machine learning in the sense that, well, the data had bias, the society has bias, the data has bias. So why blame machine learning for that? So if there is, we blame it because it reinforces it. And a third challenge is machine learning model is interpretability. So for example, there's an AI method which algorithm which tells whether or not you want to give somebody a loan, and you have millions of data. It figured out this person can be given a loan, this person cannot be given a loan. But say a person was denied a loan, you say, hey, why was it denied? And you say, the machine AI tool told it. What? The AI tool it's telling me whether or not I was denied a loan. Tell me why I was denied a loan. I'm sorry, the AI tool told it. Now that becomes an issue because you can't interpret why he was denied a loan or something else. And there could be very financial decisions too, where you need to know why. Think about it, even for a doctor, suppose the AI tool told that this person probably has cancer and this person probably must be operated for a surgery. The doctor needs to know why. Hey, why? How did you tell it? What is the background? He needs to know the causality, the cause. The doctor needs to know the cause, right? He can't just say the AI tool said it. So therefore, there's an issue of interpretability because they are black box. So most machine learning methods are difficult to interpret because they are designed as black boxes. But even then, there are some models which can be interpreted. You can design models for improving interpretability. There are ways to go about it. So it's not that none of the models are interpretable. It is possible to do some interpretability on the models too, to some extent, not to a great extent, to a limited extent. You can also have layers and you have outputs from some hidden layers. It's possible. So broadly, these are the challenges. Once again, the data requirement, and I said, though there is a challenge, but there are ways to go about one-shot and few-shot learning. It is still possible to work on less data too. And two examples are one-shot and few-shot learning. Reinforcement bias. There are also ways to look at it to make it more less of bias. There are machine learning approaches to do it. One example is in the model itself, you do not specify, you do not provide that, or you balance the model. So balancing the data is also possible. So we look at the data and see if there's a bias, and generate data, augment the data augmentation, and then you try, and so that there is no bias in the data. So there are methods possible to do it. Interpretability, there are methods also to look into it, limited methods to look into it. For example, in hidden layers, you can have outputs coming from hidden layers so that you can interpret them to some extent. So though there are challenges, there are already some existing methods to take on these to some extent. So so these are all three active areas of research, and this is machine learning is probably one of the very promising areas of research. So therefore, there's a lot of papers which have been published in these areas too. Concerns, circuit breakers. So why do as concerns? Think of the stock market crash. So because you have algorithmic trading and all, so it will kind of reinforce it. So there are examples where the stock market has crashed because of the AI tools, and it just reinforced it, and everybody started selling off, and all the AI tools are working, and it led to a complete crash because everybody was working on a large number of people were working on AI tools, so it led to a crash. So you also need to a circuit breaker. Hey, don't overdo it. So now, of course, there are circuit breakers, but there was a time when there are examples of stock market crashes too. And then concerns, because if you have algorithmic pricing, so you have machine learning based, AI based algorithmic pricing. People are pricing based on algorithms. Now, think about pricing, for example, airline pricing, So when you go on earlier, many years back, decades back, Air India would have fixed prices. So this 5,000 rupees for going from Delhi to Mumbai, something like that, fixed prices. Then things changed. They used AI, machine learning, and it became dynamic pricing, algorithmic pricing, machine learning based pricing. So the prices that you get on flights, they are all based on machine learning, algorithmic pricing. But then you have a competition policy, because how do you say that people are not getting together and creating a cartel, or maybe giving big difficulty to consumers, because when you really badly need a ticket, they are going to mint money by raising prices. So you need to redefine it in some way. So these are concerns. The third concern is accountability. Somebody says, why do you do it? The AI tool, the machine learning tool told me to do it. So why did you give a loan? Well, he told me to do it. Accountability. So somebody wanted to scam the bank, and some manager gave a loan, and the auditor asked, on what basis did you give a loan? Then the bank manager said, oh, the AI tool said it. It's not my fault. The AI tool did it. So what does the auditor do? Nothing. So you have to think about it. So therefore, it's an excuse. So therefore, it's a concern. And another concern is manipulation. So as you know, adversarial attacks, which means it's all depends on the data. It learns from the data. So if you really want to hack into it by providing it data, providing it fictitious or false data, you want to manipulate it. You give it the data which is wrong, and then it will accordingly give it a different result, because you have fed it wrong data. Something like, if you take the child and show a dog and tell him it's a cat, and keep telling it's a cat, it's a cat, it's a cat, show all the dogs and tell him it's a cat, then the child will learn it's a cat. All the dogs will become cats, because that he was told, fed the data. So if you want to do an attack, hacking on that, you can manipulate ML models too, because you fed it the data. So these are concerns, not challenges. So I move on. Okay, I believe now I'm probably really overshooting. So I'll quickly move on. There are some examples here I'll show you. And I hope this is recorded, so you will be able to look into these examples yourself. I'll quickly go across some examples to show how they run, but you can follow this. Since it is recorded, you can follow these links and see for yourself. So for now, what I will do is I'll quickly go into it and show a run on Google Colab. So here I am going on Google Colab. By the way, is it okay if I exceed the time with a couple of 5-10 minutes?
Yes, sir, it's completely fine.
Okay, fine. I apologize. I'm generally not good on the time. Okay. So this is Colab. Colab, as you know, is free, and I'm using textbooks, IPython notebook, and this Python notebook can be run openly on the browser. So you can just go on a browser and just run it. So if you want to go Colab, you just on the browser write Colab, COLAB, and then you will find a place which is free, and you can run your IPython notebooks. Why is IPython notebook easy to learn? Because IPython notebook you can run cells, code cells, as well as text. So this is text, so it explains, and this is code. So you have code and explanation of the code in the same notebook. So the same notebook which has text also runs code. So that's why notebooks are great for learning. So this is a very, very simple convolutional neural network for time series prediction. Now, You know, you have many methods of time series prediction. This is not the best example in detailed example, but it is good enough for a starter. So enough for a starter. So let me show you here. So we import some libraries. So here we are improved numerical Python library. We call it NumPy. We are importing Keras here because Keras has a deep neural network. So you can do convolutional neural network. So here what we are trying to do is this example explains how you're making a convolutional neural network. So this is a function. In this function, we are doing a deep neural network for sequential model. So we call it convolutional neural network. Now that's another course altogether, but I'll just mention what it can do. So this function can take a window size. Window size means suppose you have 1,000-day time series. So you can take a window size of, let us say, 5 or 10 days, and suppose you take a 10-day window size. Hypothetically, just to make it, you would like to have larger window size, but suppose you have 10-day window size, then on this 10-day window size you will run convolve filters. What is the filter? We kind of apply some another matrix on the data matrix, the window matrix, and you multiply them and get a new product. So we multiply them point by point. Now, and then we call it the process of multiplying these two filters and your data as convolution. We convolve it. And suppose we have 4 filters in this case. It is defaulted to 4 in this case. And then you can have more than one time series. You can have say 5 or 6 time series is possible. So if you have 5 or 6, you will have 5 or 6 outputs in the time series, which means given a long length of time series, say 10, you are going to predict the next one, the 11th one. So this conv1D is a kind of a layer in a neural network. So this takes in some number of filters which you define in the function, and the filter of length something. For example, the filter could be of length of 5 only, so 5 by 5 filter. There's the activation functions, the ReLU. So this is the activation functions which gives non-linearity. You could choose various kinds of non-linearity. ReLU is a choice because it works very fast. So ReLU is a good choice. There are many SeLU and very sigmoid and with lots of kinds of non-linear activation functions. This is the shape of the input. You say, this function accepts this kind of input. Now this has to go through a dense layer. Dense layer means all points connected to all other points. So therefore it's dense. So that you see, so that's a dense one. And you have how many outputs you want and what kind of activation. Here it's linear in this case because we just want based on if there are 10 time series, you want 10 output, so it's linear. However, for classification you can use sigmoid, and you can also do for multiclass, you would do something else, softmax, and so on. So this is giving you this is the most elementary neural network because it just has one convolutional layer and a dense layer. That's why I say just one convolutional layer. But typically neural network can work in probably dozens of layers, even hundreds of layers. So this example is just one layer, but you can even have hundreds of layers, and you can imagine how dense it can be. So, and you can have various variety of filters and activations and all to make it more non-linear. If you want to add richness to it, if your data looks to be very complicated, you can add more layers and make it more and more complicated. But you see, even the simplest one layer, it can still work. Let us see a simplest one layer. So if you want to create it, so here we run this. This was the function we had defined. Now we call the function. We're calling the function and passing it arguments. You pass it a window size of 50, filter length of 5, and 4 filters. So the previous function we saw is we are not calling it. And so therefore, when if we want to do the shape, this shows this as a shape of 51 and an output shape of 1, which means basically we are just doing one output from this from a window size of 50. So the time window size of 50 means the time series has 50 points of time. And filter length 5 means we have a 5 by 5 filter which is multiplied to the data. Now this data is good, but we have to make time series. We have to generate a time series. So why do we have to generate time series? So the big thing is the two things here we wanted to discuss here. One is time series is a different thing from traditional data because the sequence is important. We can't just take a data and shuffle it. We cannot shuffle a time series. The sequence is important. So we have to take care that whenever we do a data, the sequence remains. And you know, in machine learning, another thing is we always have to also split the data because we can't just do a training on the whole data, and we also need to test it, how well it did. And we also have validation in which we try to improve the model before testing it. So we have train, validation, and testing. So this is a fundamental difference between machine learning and econometric models because we don't do training and testing. So which means we give a lot of data to it, and it learns from the data, known as the process of backpropagation. It tries to learn from the data, and then it tries to improve the model on its own, which is known as the validation, and then it tests it on another data. So because mathematically we can, so mathematically what it means is, so this is, by the way, how we created a time series, the sample case, and we'll see more. Okay, mathematically, what it means is, given some input data, you have a prediction, and we try to, there is an error in the prediction. So we try to minimize the error, so the error becomes 0 or close to 0. What is the, so we try to change the inputs, the coefficients, so that the error becomes 0. And in order to do that, what should be the coefficient so that the error is 0? The loss function or the error is 0. So what we try to do is, so if we just train it, it can overfit because mathematically it will find all the coefficients and it will make overfit. So therefore, in order to do this, we also need a testing. So let's see here. Here we just generated toy data in which 1, 2, 3, 4, 5, 6 like that. But this point, line number 12, is the important one. Test ratio. So this line says X train, Y train, X test, Y test. This is a fundamental thing is we need to split the data into training and testing. So we train it on one and we test how well did it do. Now, and the big issue is if we just train it, then it will always be 99.99 or 100% accurate. Why? Because we use the data, it learned everything about the data, and it will always be accurate. For example, if you give a child 100 types of pictures of cats, and it will learn from the 100 pictures the cat, what a cat is like, and then you pick one of those 100 pictures and show it to the child will be 100% accurate because it has learned from all the 100 pictures. So if you give the same picture, it will give 100% result. So you have to give it some other picture to find out how it behaved, how accurate it was, some other picture. So therefore you have to split the data into training and testing and then see how well it did. Therefore you have to do training and testing. And for validation, what we do is you give it some other data and then you change the model. So give it unseen data and then change the model. Okay, it didn't learn it, let's change it, tweak the model. So you tweak the model based on that. And there is a layer of learning known as learning rate, because when you give it new data, it will learn something and change the model, but it cannot change the model completely, right? So there is a learning rate. At what rate will you learn new instances? So this is why machine learning is so different, because you have training, validation, testing, and then it keeps learning. There's a process of learning from the data, and all of this is automatic. Now, in this case, this is how trading looks like. You fit the model. So now you have a model defined, and you give it a data. Then it periodically it keeps on checking. So you see in this case, in the first epoch is when you train over the whole entire data set once. That's called an epoch. So here it found the loss is when it is related to your error. The sum of all those errors is the loss. So now if you look at this, the aggregate of all the errors is your loss. So we call it a loss function. The aggregation of errors need not be the sum. It could be. Now in this case, it says that the validation loss is this, and the accuracy is the average accuracy is this. Now it showed that now in this case, average error is this. So in the first case, the validation error was 16.665. Now in the next case, it learned and decreased the error to 11. In the third epoch, or the third pass of the whole data, it decreased to 10. But in the fourth one, the error increased to 16. And the next one, it fell down. And then it fell down. Again increased and fell down. But you look at it, initially it was 16, but if you look carefully, over time it came down to just 1. So it mostly falls and then slightly rises and then falls. So what's happening is it is improving over time broadly, because it is going through different passes of the data and trying to decrease the error. Remember what you do in regression. When you do it in regression, your calculation of your you throw it a data and give it through the mean squared error. You find out what is the RMSE, root mean square error, and then you try to fit a curve to the data, and that's a closed form. So you don't do it. So if there are iterative methods too, you can also do Newton Raphson's and all this fitting of the curve, but you don't take in new data and you don't validate it, change the model based on new data. You don't test it with different data. So the process of training, testing, validation, if you do it, then that's machine learning. So here, in this case, you're training, validating, testing, and periodically it keeps on changing and on. So which means if you give it many epochs, let us say 1,000 epochs, then the validation will keep on falling and the model will be more and more accurate. Maybe 99.99% accurate. So which is deadly accurate. But the point is, we don't really need deadly accurate. It may be an overfit. It is too much fitting the data. So therefore we have to test it. And we have to give it unseen data. So too much of accuracy is overfitting. So therefore we have to see the curve, plot the data and see, did it overfit? So there are methods to see that too. And this is how the model summary looks like. This is a very, very elementary model with just the convolution, one layer of 1D. So there's very elementary. But even with the elementary model where our data was just predicting, we had given it some values like 9 and 1, 2, 3, 4, 5, 6, 7, 8. It's just a time series. No, there is elementary time series. And then the values after that will be something like, after 1, 2, 3, 4, 5, 6, 7, and 9, the next is 10. So however, when it does through a model like this, it won't give the exact value. It will give something close to that because as we find out, so it is predicting 991.33, 992.33, something like that. It's predicting the next one, but exactly close to it. So this is an example. What I'm trying to say is how these models can work with the simplest one layer neural network. And why did I show it? I showed this to tell you that how in this case, it is not just once running the model and finding out RMSE or best fit. you are doing a series of the sequences of these iterations, and you need to do a testing, validation, and splitting so that you can change the model too. So that's something unique in thing. So what means is you're not only running it iteratively process, you can also tweak the hyperparameters. You can also tweak the model. It's not just that you are uh, running it and just testing it, running it multiple times. You can also tweak it in the model by validation. So the model can also be changed. So not only are the coefficients learned again, the model can also be tweaked. So that is what makes it so different. And in these models, you can add nonlinearity of your choice, deeper models. In this case, this is an example of just one layer. You can have many layers and many detail as you want. Now this was one output. Now in this case, you can have multiple input, multiple outputs. So we have multiple time series. So what would you do? So similarly, just like one layer there, one input there, you can have multiple output like this. This is an example. Again, you will split them into training and testing and validation. Again, you can run them like these. It will fit it, and also try to learn the best fit. And again, it will also try to change the model so that it can work better. It will improve the model, and then it will try to make a prediction. So this is again with a single layer, but it takes both input and output. So the point I'm trying to drive home is that it is possible. This was just a one-dimensional CNN, just a single layer, to show that that's how a neural network tries to learn, make an estimate. But the key thing here is it learns and changes not only changes the coefficients to be learned, the values of the coefficient it learned, but also it can modify the model. That's what makes it so interesting. So I'll move on and come back to this one. I know I've overshot time. The other one is dimensionality reduction. So I'll briefly go across dimensionality reduction. So in dimension reduction, what you have is something like an autoencoder. So you know the PCA is perfect, right? In PCA, principal component analysis, you can just reduce the dimensionality to any extent and very well, and it is a closed form. So given an input, you will always get the same output. It is not learned; it is closed form. So PCA is very accurate, and it is really the best performing thing because it's very accurate. But PCA is not scalable, which means given that you have 10 variables, you can do a PCA very well. Suppose you have 10,000 variables. Your machine can't handle it because there are too many, 10,000 by 10,000. Think of the covariance matrix. It will be a very large covariance matrix. You will run out of memory, you will need days to solve it. You will run out of memory. It is not scalable. PCA is great, but it's just not scalable, because the covariance matrix is too large. So you would need some other methods to handle these kind of things. Now, you also have singular value decomposition, but you also have something, but PCA is inherently linear. It's not non-linear. So now autoencoder is another one which is scalable and non-linear. So autoencoder obviously won't be as accurate as PCA, because PCA is closed form. An input and output, mathematically it will give you the exact output. But it's linear, it's not non-linear, and again it is not scalable. So if you have a large number of variables, you can do an autoencoder, and it does pretty well. So let me show you just the output. Here is some code, and what autoencoder does, it has an encoding layer. It encodes, reduces it to a lower dimension, and then decodes. So the idea is, given an image, if you're given an image, or I'm telling an image to, you can think of your financial data too, but just to say it like that, suppose you have an image of a cat and it reduces the dimension in a lower dimension, and then it increases, reconstructs the image back, and then it sees how good was the reconstruction. It sees the reconstruction error, and it tries to minimize the reconstruction error. So it tries to learn how to minimize the reconstruction error. So therefore, in your financial data, given a data, it will try to change it into a low dimension and reconstruct the data back and try to minimize the reconstruction error. And therefore, it tries to learn how to minimize the reconstruction error. So therefore, there's a learning here. Therefore, there's a deep learning. It's a machine learning method. And therefore, and given it any thousands of dimensions, because some data can have lots and lots of dimensions, many variables, then PCA would be a bad choice because too many variables. In that case, do the autoencoder. And in this case, once again, this is the data. So this is a data of, I think, yield curves in finance. So this is a 1 month, 2 month, 3 month, 6 months, 1 year, 2 year, until 10 years. So these are interest rates for a year. This happens to be a bad time, as you know, the yield curve is going this way. It should be rising, right? So it is falling in this way, probably a bad time. Now, so these are the yield curves. And if you look at year-wise, these are the yield curves. So if we have to do PCA, obviously it will be good, but it will take a lot of time. So this is the reconstruction error for this is the error for PCA. These are the components, how they are resolved. Only 3 components. And PCA, you have another issue too. You have to pick up the number of constants or components. Now, if you choose just 1 or 2 components, then your quality may not be good, but more number of components you will be doing better. Now, you of course have ICA too. Now, this is how the autoencoder is working. And let us see the comparison. Now you see, obviously PCA is perfect closed form, but look at this. You have a basic linear basic autoencoder, and also you have a deep autoencoder. The red one is the basic autoencoder, and the blue one is the deep autoencoder. So you can see the deep autoencoder, though it still does pretty well. So it is possible to use autoencoders for deep autoencoders for these works of dimensionality reduction when you have large number of variables. So the reason I quickly went to it is just to give a brief idea that, so time series, when you have a prediction, you are using a supervised method. Dimensional regression is a non-supervised method. So that's why I showed you 2 examples of one each of supervised and another non-supervised. Very elementary methods, but so that you have a broad idea about how learning happens. So the last 20 years there has been a lot of papers published in finance and economics, but not too many. I see from Google Scholar about 145 papers on stock prices, 53 papers on risk, 50 on banking, 35 on credit, and so on. So these are on Google Scholar, when I put the keywords deep learning, finance, economics. So these are the papers which have been published, but these are not too many, as you can see. So few relatively. Huh?
Can you please speed up the process, because we have the Q&A session and the
right. So this is perfect. This is the last 2 minutes. So, and then these are like published methods, most of them LSTM, because there are sequences, and then now this is the last slide, connecting the dots. So why we see the minimum least, we see that we have learned that we know that we have minimizing least squares, maximizing likelihood, maximizing a posteriori. This we have already learned. This is how the estimates are done. But there is also the learning part. If you have to learn from the data, how would you proceed? How do you learn from the data? These are the methods of estimation, but you also need to do a learning. So in basic regression, if you use regularized regression, then you can do some learning. So you can extend basic regression methods by adding ridge, lasso, elastic net, and do some cross-validation. If you do this, then that's also machine learning. So it is possible to extend it and bring in machine learning. So the focus in machine learning and deep learning is generalizing. How well do you generalize? Because mathematically you can minimize the loss function, minimize the error to go to close to zero, so it will learn perfectly, 99.99% accuracy. But how well do we generalize? And the last thing is transfer learning. The best part of machine learning is, given that you have a model which has learned a lot, let us say a model that we have learned from the stock exchange S&P 500 prices. It has learned from aggregated indexes. Now that learned model can be used on some other data. So that's something which is very powerful and which is not there in econometrics, which is you can save a model which has been trained on a large number of humongous amount of data and reuse the model with some model which requires less data by fine-tuning the last few layers, because deep learning has a lot of layers. So suppose there are 50 layers. So you can last 5 layers you can leave it and fine-tune with specific data. So you have some data of some other data which you can use for a particular area. That's known as transfer learning. And that is completely different and very, very powerful in these days. So I mean to say, what I beg to offer is that please consider that these are some methods which are available, particularly deep learning, transfer learning, which have not been used in econometrics. So if econometrics embraces transfer learning, for example, it will be a great, it will be of a lot of importance. It will give a lot of significance in econometric analysis too. So to connect the dots, in econometrics and machine learning, I would say that econometrics should embrace these machine learning methods too. So though they are challenging in terms, but actually I would say these are methods, so they can be used too. So we should try and these new methods as much as possible. So that's all I have to discuss so far. I apologize for overshooting the time significantly, but please ask any questions that you have.
Sir, we already have 3 questions in the chat box.
Wonderful. Let me go back to your yes. Stop presenting. I stop presenting and go back to the chat. Great. So I see Pavitra Devnath. How do I interpret a result logically in my research paper that I got from ML? Wonderful, Pavitra. This is wonderful. This is a very good question. Now, it depends on the task. If your task is, for example, classification, then in order to do that, you would present results such as the confusion matrix. So when you do present a result with the confusion matrix, which is a metric, you would say in the confusion matrix, this was the F1 score. So there are metrics to show how well, because you have already split the data into training, validation, and testing. Now the test results will show, because it is unseen data, and you have a confusion matrix. So you have a ready way to show logically that your machine method worked. Similarly, this is a classification. You could have regression, you could have clustering, all have different metrics. So in machine learning, establishing a result is through metrics such as these. I hope I was able to answer your question, Pavitra.
Yes, sir. So,
Wonderful. So if you have a specific use case, you can email it to me. I can see that, that's for sure. But that's a very
okay,
good
sir. Okay,
question.
sir. It was for supervised learning only, for instead of
Oh,
logistic
wonderful.
regression.
Oh, great. So if it is supervised learning, you use a confusion matrix and you have some scores such as F1 score, another, so another more. So you can, so confusion matrix is the best way to establish your result. Very good question. And then also you can show a variety of databases, a variety of methods, and then all their confusion matrices. You plot it in a table. These are the databases I've used, so that you don't show a bias towards a particular database. You show it, and then you have a various method models, so you don't have a bias towards a model, and then all the confusion matrices. Then you plot them, and then you show them that these are the results in the confusion matrix. So you have used test data too. Very good question. I think Swarnanil has Memela certain challenge. I don't know what is in particular. What do you think to take? Oh yes, good question. So Swarnanil, it's a question is if ML can machine learning can overcome these challenges, don't you think it will kill roles like data analyst and data scientist? Very good question. So 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 the thing is some data, yes, some even for the challenges, the challenges, there are approaches to the challenges, but the truth is different kinds of, so suppose you're working in a company, in a finance company or engineering company or some kind of company as a data scientist, suppose you're working there. So when you really work in real life data, you'll find there are not just 4 or 5 variables, there are thousands of variables, hundreds of variables. In real life, data is not just 4 or 5 variables, there are many, many large number of variables. And real life, you will find out that they are complicated relationships. Now, when you have this kind of relationships and this in data and you have machine learning working, you will find that the domain also has its own challenges. If you're working in medical field or finance algorithm trading field or some kind of company, the domains have its own challenges. So the data scientists, so these tools and methods are kind of give you a background of how to use this, of what to use, but how to use it, where to use it, have their own challenges. So the data scientists and data analysts always will have a role to play, because the models will keep will present its own challenges, and you will have newer methods developing, and this field is developing really fast. So even keeping pace is too difficult. So I think the data scientists and the data analysts have their jobs are safe for at least 1 or 2 decades, at least. I mean more, because they have a they have a relatively safe job for maybe a couple of decades for now, I think. Very good question. Was I able to answer your question, Swarnanil?
Yes, sir. Yes, sir.
Okay, thank you. Koel, what would be the likely impact of machine on structural unemployment? Okay, for the next 5 to 6 years, when the AI sector is expected to grow by approximately. Very good question, Koel. The interesting thing is, who is a data scientist is difficult to know these days. But the truth is, many people are already started doing data scientist work. They may not be classified as a data scientist. They're already working. I mean, change their roles. So even maybe it is possible that an econometrician in a bank may be doing a data scientist job. It's quite possible. So it is no longer a position. A data scientist necessarily has to be a position. Not so. Maybe a data analyst working in some company, bank or something is already doing machine learning thing. And yes, it is true that it's going to be a huge impact, because that's because these days in your profile, in your resume, if you have machine learning, deep learning or something, it's going to sell. Somebody is going to take a look that this guy knows machine learning, deep learning, has done some projects, that he is going to sell. So they are really going to like it very much, because most likely they are already trying to implement it or have implemented it. So therefore, it is going to have a big impact, I think, on employment. And if you don't know, then you're probably missing out. So it's going to have I think there's going to have a significant improvement, impact in this kind of thing, on these kind of jobs. Obviously, there are some kind of jobs which doesn't relate to analysis, but those kind of jobs which involves data, it's definitely going to have a huge impact. Was I able to answer this question, Koel?
Yes, sir.
Good question.
Thank you, sir.
Now I would like to pass on the baton to Ms. Ishita Mukherjee for the concluding remarks and vote of thanks.
Thank you.
Good evening to one and all. As we approach the end of today's session, it is with immense pleasure that I would like to extend the vote of thanks to Dr. Sujit Chakraborty for his effortless contribution to this session. While his knowledge about the field of machine learning and econometrics is valuable, he has tried to effortlessly curve and impart bits and parcels of the same into this session, and we are only grateful for your continuous patience in this regard. Though through his elaborate case studies, he has not only tried to connect us better with the world of deep learning and data sciences, but has also delivered a better comprehension of the contrast that is inherently present between machine learning and econometrics. Furthermore, we are thankful to him for his acknowledgement of the questions posed during the session. We are all relevant to the saying that knowledge is of no value unless we put it into practice. And today, yet again, we have all got a taste of the same through the many virtues of data. Additionally, we are thankful to our senior, Mr. Ashay Wadhwa, for his continuous support with our sessions. We are grateful to the coordinators and the audience present today, without whom this session would not have been a successful one. Thank you so much.
Thank you all, and please feel to stay in touch if you have very, very good questions. And there's a quick question here from Koel. I'll just take it on. What will be the likely impact? Is it the same question?
Yes, sir, we have already taken it.
Thank you. Thank you so much, and please stay in touch, and thank you for inviting me, and wish you all the best in your careers. Let's hear that you are some of you are getting into data scientist roles, and let's hear that you are going great for all this. And great job. Well done. Thank you, placement, Sil and Sornanil and everybody. Thank you.
Thank you, sir. It was great having you. Yeah.
Thank you. Bye.